Hi everyone and welcome to the Linear Law series. Today we will be doing the following. I will introduce to you what linear law is, why we should study it. We will also learn how to convert nonlinear equations into linear equations, and we will also learn how to convert a linear equation into nonlinear equations using certain examples. Before I begin, I want you to think more about what does the word linear law mean. Okay, the word linear actually just means straight line, which I hope gives you sort of a tune in or a tune in into what this chapter really is about. What we are really trying to do here through linear law is to convert a non-linear relationship in curves into linear relationships in straight lines. Now, let me give you an example to illustrate what I mean. Some of you who study physics, you may have encountered this curve before. This is actually the pressure versus volume curve for ideal gases, which tells us that as the volume of the gas increases, the pressure actually decreases for a constant temperature. And this particular graph can be modeled by the following equation: pressure equals to 1 over volume. Now, how do I convert this into a straight line? You realize that I can do this by easily changing the axis into pressure against 1 over volume, which will actually give us a linear straight line, a y equals to x linear straight line. So you realize why we want to do this is because sometimes if we are able to find a linear relationship between the variables, scientists have actually found that it's so much easier to form relationships when it seems like the variables or whatever they're trying to measure are linearly related in this manner, meaning along a straight line. And that is why you will find that linear law is actually something that is very useful in scientific methods. So, because we're going to be dealing with a lot of straight lines today, I want to quickly recap on some of the things that you might have learned before in Amaths. So we will know that all straight lines have the equation y equals to m times x plus c. Okay, where m is the gradient and c is the y-intercept, meaning the place where the line actually cuts the y-axis. Now notice how I change it into capital Y and capital X. Now I want you to just hang in there with me first, you will find out why later. Okay, next we will talk more about the formula for gradient. We know that the formula for the gradient is given by y1 minus y2 over x1 minus x2. Either that or it can be y2 minus y1 over x2 minus x1. Both will give you the same value. Okay, and lastly, how to find the y-intercept given two coordinates, the coordinates of 2 points lying on the line. First step, you can find the gradient using the formula as you have seen earlier. Second step, okay, you substitute the value of m and the coordinates of either one of the points into y equals to mx plus c, and then you can solve for the value of c in order to find the y-intercept. Okay, so now before we begin on linear law, I want to bring you back to some of the quadratic curves, some of the curves that perhaps most of you are familiar with. Now you have seen this curve before, y equals to ax squared plus b. I want to plot it out. It will actually look something like this. Now, what happens if I want to obtain a straight line? Okay, I want you to study this particular equation I've given you over here. Is it possible for me to express this in the form of the straight line equation y equals to mx plus c? Or in other words, how can I change the variables of the axis over here so that I can obtain a straight line? Maybe I give you some time to think about it. Please pause the video and think about it. Okay, I hope you thought about it. Okay, now you realize that to convert this into a straight line equation, all I have to do is to use these variables y against x squared, plot the line y against x squared, and actually you realize that you can easily get a straight line with gradient A and a y-intercept of b. That's how I can actually convert this curve into a straight line, for instance. Okay, so you realize that in this general equation, to make it more obvious for you, I'll show it to you. This actually is now our big Y. See, this is where I'm introducing the capital Y now. This A is our gradient, which is M. X squared becomes the big X, and B becomes the Y-intercept. Okay, I hope you are seeing this relationship now. Okay, so quickly, In linear law, I want to define for you what the big Y, M, big X, and C in means actually in the equation that has already been converted into a straight line equation. Y actually refers to the variable on the vertical axis. Okay, so if I have to go back, do you realize this big Y here actually refers to the vertical axis? And of course, you can guess then that big X actually refers to the variable on the horizontal axis. Okay, now Y can be expressed in terms of X or Y and or Y only. Okay, for instance, X over Y, 1 over Y, log Y. These are all examples of your big Ys. Okay, take note that these are all in the equation that has already been converted into a straight line form of equation. Okay, big X is the variable on the horizontal axis. The horizontal axis, it must be in terms of X and or Y only. Okay, so take note that these are the few examples, okay, typical examples of what big X can be. Now, why do you think we do not accept all these into big Y or big X? Let's take a look at the first example. You notice that there is a over Y over here. Okay, usually we do not accept big Y with constants in them. Okay, usually we only accept it as 1 over Y without any constants. Same for negative log Y. Because of this negative, we cannot accept it a as a big Y. And lastly here, because b is multiplied to y plus x squared, this b here makes this a very invalid form for big Y or big X. So take note, big Y and big X must only be in terms of small x or small y only. How about M and C? M and C is actually the gradient of the straight line. Notice that gradient is a constant, means right, it cannot contain any small x or small y. So these are a few examples of what a gradient can look like after it has been after the equation has been converted. Same for C. C is actually the big Y intercept of the straight line and is only in terms of constants only. Okay, so I want to give you a few examples, okay, and in the following examples, I want you to try and identify big Y, big X, M, and C. Okay, so let's take a look at part A. I think in part A it's pretty obvious that big Y is actually Y minus X cubed, big X is X squared, M is the gradient, which is A, and C is 4. Okay, notice, how do I know that I have to, how do I know I'm correct? Okay, let's check. Is Y in terms of X and Y only? Yes, there is no A, there is no constant in there. How about X squared? Same. Gradient is simply just in terms of a constant. C is equals to 4, which is a constant. So that is correct. Now let's take a look at the next example. Is it possible for me to identify big Y as 3Y? Okay, it is actually possible, but actually for it to be more correct in that sense, actually, what we will do is we will divide 3 to each side of the equation to get Y equals to 7 over 3x squared plus 20 over 3. Okay, I think now for you it's very obvious to identify what the big Y, big X, M, and C is. Big Y is just small y, big X is x squared, M is 7 over 3, and the big Y intercept is 20 over 3.